Hi everyone. In the previous lectures, we discussed about transfer functions and we discussed about poles and zeros of the transfer functions. We said that the knowledge of the poles and zeros of a transfer function tells us if a system is stable or not. We also said that the knowledge of a transfer function is fully sufficient to know everything that one needs to know about an LTI system. We said that stability can be guessed by the knowledge of poles and zeros. And then we said we can find the frequency response by evaluating the transfer function at s equal to j omega. Now once we know the frequency response, we know the response of a circuit for any input. Okay, any input which is Fourier or Fourier series or Fourier transform representable. So that's why finding transfer functions for circuits is of great importance. Now what we are going to do is, of course, when the circuit is more complicated, then we have to rely on simulation softwares, because writing equations and deriving using KCLs and KVLs, the analysis becomes too mathematically cumbersome. So then we have to rely on a simulation software for that. But then most practical circuits that we encounter in practice can be analyzed using intuitions. So we can intuitively write the transfer function of any most of the single stage amplifier circuits by inspection of the circuit. So that's what in the next few lectures we'll be trying to build that in intuitive methods or simple procedures to derive transfer functions. Okay, so again transfer functions means you have to find poles, zeros, and the gain of the DC or the high frequency gain of the system. So we'll be first trying to find poles, then zeros, then how to write a transfer function for a simple single stage amplifier circuits. So first, shown here is a simple common source amplifier. So wherein you have a current GMVI which is flowing through an impedance. So the gain of the circuit is simply given by GM into Z of S. So the frequency dependence of this circuit is entirely not because of the MOSFET. So the transconductance is assumed to be independent of frequency, but the frequency dependence comes because of the impedance that you connected at the output. Of course, this impedance will also have the parasitic capacitance of the MOSFET, okay? But the transconductance itself is not frequency dependent. I can club all the parasitics of the MOSFET into the impedance Z here, and then say that the frequency dependence is arriving entirely, the frequency dependence of this circuit is entirely because of this impedance Z. So the poles and zeros of this transfer function is same as the poles and zeros of the impedance. Okay, so that's why at least in the next 3 lectures we will focus on writing poles and impedances for simple poles and zeros for simple impedance networks. Okay, of course most engineers will be aware of intuitively, they'll know how to write it, but again we'll try to give some life to those intuitions in some simple procedures. So that's what academic pedagogy is all about. So that's what we'll be doing in these lectures. So first, this is a result we'll be using often in this lecture. So if let's say we have two impedances Z and minus Z connected in parallel, then the effective impedance offered by the combination of these two impedances in parallel is simply infinity. Okay, the impedance here is infinity. We already discussed this in one of the previous lectures. The way in which you show that it's infinity is you can write the expression for the parallel equivalent, which is Z into minus Z by Z minus Z. That gives you infinity. Or you can see in an intuitive way that if you apply a voltage source Vx and measure the current that Ix, which is being drawn by the circuit, we can see that if the impedance Z is going to draw some current from Vx, minus Z is going to supply that current back. So the net current that is drawn from the voltage Vx is 0. So you applied a finite voltage, but the current drawn is 0. So therefore, as far as the voltage Vx is concerned, this combination of impedances Z and minus Z is going to look like an open circuit. So the impedance will be infinity. So this is the result we'll be using throughout this analysis. And what happens in frequency dependent circuits is that this condition of impedance becoming negatives of each other happens only for one value of S. And that value of S is what we'll be referring to as pole. The value of S for which the transfer function in this case happens to be impedance blows up to infinity. So first we'll consider a very simple two parallel impedance structure. So this is something we'll be commonly encountering. As we will see, when we go to some example circuits, we'll see how to find poles for that. So this is a standard impedance that one will encounter. So when you have two impedances in parallel, our goal is to find the poles for this. So I have written here the parallel impedance, which is Z1 Z2 by Z1 plus Z2. So for this impedance to blow up to infinity, the condition that has to be met is Z1 plus Z2 should be equal to 0. Now mind you, Z1 and Z2 individually they have to be finite. Okay, Z1 and Z2 cannot be 0 individually, but the sum of the two has to be 0. That simply translates to the condition that we just discussed a few moments ago, which is nothing but Z1 should be equal to minus Z2. So that's the condition. We said that. So then at one value of S, so for some value of S, this condition will be satisfied, where the impedance Z1 will be negative of Z2. Then that will be your pole. Okay. Sometimes this condition Z1 equal to minus Z2, we can also rewrite this as Y1 equals minus Y2, where Y1 and Y2 are admittances of the impedances Z1 and Z2. It's just Y1 is 1 by Z1 and Y2 is 1 by Z2. Okay. The other condition by which we can find the poles is by equating both the impedances to infinity. Both Z1 and Z2 should be simultaneously infinity at a single value of S. That can also give us the location of pole. So these are the two conditions. When you have two simple branches of impedances, then you can use this condition to find the poles of this impedance network. Okay. The second problem is where we have two impedances in series, Z1 and Z2 are in series. Now we are supposed to find the poles for this network. Now the condition obviously is that if one of the impedance blows up to infinity, then the overall impedance is also infinity, because they both are in series. The impedance is Z1 plus Z2. Okay. So this series impedance should be infinity. That condition is satisfied if either one of them is infinity. Okay, at some value of SP. So that's what I've written. The first condition, you can find a pole by equating this impedance to infinity. So then the value of that we call it as SP1. And similarly, Z2 can blow up to infinity at some other value of S. So that will be the second pole of the system. Okay. Now it can happen that both of them can blow up to infinity at the same value. So then the system will have a one pole at that value of S. Okay. So this is a combination of the first two cases that we discussed, wherein we have a network now of one impedance Z1 plus Z2 in parallel with an impedance Z3. So we can apply the same conditions that we applied before. So to find the pole in the system, this entire impedance Z1 plus Z2 should be equal to the negative of Z3. Right? The same way when we had just two of them in parallel, it's a similar condition. So this entire impedance in this branch, the first branch, which is Z1 plus Z2, should be equal to the negative of minus Z3. So if you satisfy this condition, the value of S that satisfies this condition will be a pole in the circuit. Okay. The other conditions which will give us poles for this circuit are that since we have both the arms, where there are two arms in this, there are two parallel arms in this circuit, in this impedance. If say Z1 is infinity, then obviously the impedance of the first arm is going to be infinity, and Z3 is also infinity at the same value of S. That will also be a pole. Okay. Z2 can be finite, but if Z1 is infinity, then the first arm is going to be infinity, and at the same point value of S, Z3 is also infinity. Okay. In that case, that will give me a pole at S equal to SP, wherever this condition is met. So same way I can apply, instead of Z1, Z2 can be infinity, where Z3 is infinity and Z1 can be finite. So that will also give me the pole. Of course, I can have one frequency or one value of S for which all the three impedances can be infinity. Okay. So that will also give me the condition for pole. So using this, we will try to derive poles for some very simple networks, some very familiar networks, impedance networks that we will commonly encounter in simple low frequency, or even we will also look at some very simple resonant loads. or RF frequency loads. So the first circuit is a simple series RC circuit. So this circuit is obviously very, very simple. So you might as well write an equation and find the poles and zeros. But as you will later see that when the circuit becomes slightly complicated, the procedure we discussed will come in handy there. So first we have a simple series RC circuit. We are supposed to find the poles for the circuit. So since both of them are in series, we just have to find the condition where either one of the impedances blow up to infinity. The first one is a resistor. Resistor will never blow up to infinity at any frequency, so I can ignore that case. The second case is a capacitor. The impedance of a capacitor 1 by SC, can it blow up to infinity? Yes, it will blow up to infinity at the value of S equals SPU equals 0. So which means this circuit has a pole at DC. So you can see this is a simple resistor and capacitor in series. So at low frequencies it will behave like a capacitor which has a pole at DC. Now this circuit is two impedances in parallel, R and C. Okay. So since both of them are in parallel, if you are supposed to find the poles for this circuit, then the condition that we have to use is that we can see that both the impedances will not go to infinity simultaneously. Okay. One of the conditions, if you recall, Z1 equal to Z2 equal to infinity. Both should go to infinity at the same value of S. Then we can say that is a pole. But that will never happen because resistor is always constant. Okay, so that will never blow up to infinity. If R is finite, so that condition is ruled out. The other condition is Z1 equals minus Z2. So that's what I've written here. R equals minus 1 by SC. Then S becomes equal to minus 1 by RC. So for this value of S, okay, this impedance network will give me an infinite impedance. So I just have to equate R equals minus 1 by SC, I'll get the location for the pole. Okay, then it will obey the condition Z equal to minus Z. So we know that those two impedances will then blow up to infinity. But the parallel equivalent of those two, R and minus 1 by SC, will blow up to infinity. Okay. Yeah. So here the dependence on frequency is coming because your capacitor is a frequency dependent, or in this case it's a dependent on the variable S. So the impedance of the capacitor is variable. So that's why we are having poles and zeros and all that. With a purely resistive network, we will not be having poles in the circuit. The next circuit is a resistor and inductor in parallel. So again, we'll use the same condition. Again, if you look at it, I can't use the condition Z1 equal to infinity and Z2 equal to it. Both of them should blow up to infinity simultaneously. So that will never happen. Okay, resistor is always fixed. Inductor will blow up to infinity at omega equal to infinity, but then or S equal to infinity. I can say the impedance of an inductor is SL1 in this case, and this is going to blow up to infinity at S equal to infinity, but then R is always finite, so I can't use this condition. Okay, I have to use the other condition, which is equate SL1 to equal to minus R1, so which is Z1 equal to minus Z2 condition. From that we get the pole for the circuit. So in this case it will be minus R1 by L1. So similarly, when I have two parallel impedances and they happen to be inductor and capacitor, in that case I'll use a similar condition, SL equals minus 1 by SC, and in this case you will be getting purely imaginary poles. Okay, it will be of this form, plus minus j omega naught, where omega naught is 1 by root LC. Okay, so this is a pair of poles, unlike what so far we have discussed real poles. So this is a pair of imaginary poles. The other network now is we have one RC in parallel which is in series with the capacitor C2. Now we are supposed to find poles for this circuit. To find the poles, we can use, since there are two impedances in series, any one impedance blowing up to infinity will mean that the overall impedance is also infinity. So the first condition is, can Z1 blow up to infinity? That will never happen. At least, we'll come to that condition as well. The first condition is when Z1 blowing up to infinity. Z1 here is nothing but R and C in parallel. So you have R and C1 in parallel. Now this combination can blow up to infinity if R is equal to minus S1. Okay, so then that location of the pole, from that we get the location of the pole to be minus of 1 by RC1. The other condition is the second impedance blowing up to infinity. Can that impedance blow up to infinity at any point? Z2 being infinity. So these are like two impedances in series. So I'm using the condition of Z1 equal to infinity at some value of S, and Z2 equal to infinity at in this case it's a different value of S. We'll see that. So can Z2 become infinity? So then in that case I just have to substitute 1 by SC2 equal to infinity, and then the location of the pole happens to be 0. So this circuit actually has two poles, one at S equal to 0 and one at minus 1 by RC1. Okay. So next we have a circuit like this where it's a parallel RC circuit in series with a resistor R2, and we are supposed to find when is there a pole for the circuit. The pole for this circuit will be when the impedance either Z1 should go to infinity or Z2 should go to infinity. Okay, I just forgot one point. So if you recall the previous circuit, we said that the third condition is both of them going to infinity at the same point. We just saw that the first impedance goes to infinity at one frequency, one value of S, which is minus 1 by RC1. The second impedance goes to infinity at 0, S equal to 0. So they both are not the same points, so I can't apply the third condition. The third condition, we said when we have two impedances in series, is Z1 equal to Z2 equal to infinity at some same value of S. So that condition cannot be applied because it doesn't happen at the same value of S. So in this example, in this circuit that we are discussing now, to find the poles of the circuit, so first I can equate Z1 equal to infinity. That's a very simple condition. Simply R1 will be equal to minus 1 by SC. Then the first impedance is going to blow up. So this impedance is going to blow up to infinity. So then the overall will also blow up to infinity. So using that we get the pole as 1 by R1C. Now the second condition, Z2 equal to infinity, that will never happen. Okay, that will never happen because R2 is always fixed. So I can't use this condition. So this circuit has only one pole. So general rule of thumb is that if you have n capacitors in the circuit will have a maximum of n poles, and it can also have less than n zeros. Now here again it's a series equivalent of two impedances, series of two parallel impedances. So we'll use the same condition. Z1 is infinity, so from that I'll get the pole as minus 1 by RC1, the first pole as minus 1 by R1C1. Second condition, Z2 is infinity, this impedance blowing up to infinity, that happens when 1 by SC2 is minus R2, or the second pole is at minus 1 by R2C2. So we see here there are two capacitors, so we are having two poles here. Okay, I don't even have to apply the third condition. I know that I've already gotten two poles, so I'll definitely not have the third pole, because at max you can get two poles only for two capacitors. Okay, so and you can obviously see the conditions where both of them are blowing up is not the same. Okay, so the third condition doesn't even arise. Now we have an impedance of this type. So this is a very commonly we'll see this impedance actually arrives in many single stage amplifier circuits, and also this is a very commonly occurring impedance in phase lock loop circuits. So it's called as the type 2 PLL, where we get this impedance structure. So here we are supposed to find the poles for the circuit. So to find the poles for the circuit, we'll use the same condition, which is Z1 equal to minus Z2. So the impedance in this branch here on this side of the circuit, which is R plus 1 by SC2 equal to minus of 1 by R plus 1 by SC1 here, okay, equal to minus of 1 by SC2. When you equate the two, then you get the location of pole as minus 1 by R into C1 parallel C2. Okay, here C1 parallel C2 is C1 C2 by C1 plus C2. Okay, now we'll try to apply other condition, because we have two capacitors here. Since we have two capacitors, then at max we can have two poles. So we'll see if there is other pole in the circuit. The other condition is that whenever we had impedances of this type, we discussed Z1 going to infinity and Z3 going to infinity. Okay, both of them going to infinity, that is 2 of the impedances going to infinity. And that happens at a single value of S, that is if you look at this arm here, at DC, the capacitor C1 impedance will be blowing up to infinity. At the same value, the impedance of C2 will also be blowing up to infinity. Okay, so at DC, that is at S equal to 0, we can say this circuit has a pole, because both the branches, so if you see the second branch is R and C1, so this impedance blows up to infinity, and this impedance also blows up to infinity because the capacitor C2 impedance is 1 by SC2. In fact, since you know basic circuits, you can know that this circuit at low frequencies, I can ignore the resistor because capacitor will dominate. The impedance is going to be much higher. So that will simply be C1, and the circuit will simply reduce to a parallel of capacitors C1 and C2. So that's why I wrote an impedance like this, 1 by S into C1 plus C2. Will that be equal to infinity? Yes, it will be equal to infinity at S equal to 0. Okay, so we have 2 poles in the circuit. That's it. So this is how we find poles in the circuit for simple impedance structures. The next lecture we will focus on finding zeros for simple impedance structures, and after that we will start writing the transfer functions.